Okay, so I'm recording. Okay, so we are discussing these scheduling algorithms, and we have discussed two algorithms till now. One is first come first serve, and the other is shortest job first. So in shortest job first, we understand that uh, if there are multiple processes waiting, then and the scheduler has to decide which process to schedule, and then that process which has the shortest CPU burst, that will be executed, or that will be allocated the CPU. Now, of course, once and we saw a few, we worked out a couple of examples, and one key. So if you see here, so if with every process there is a CPU burst time which is estimated. What is the next CPU burst time? And based on that, the scheduling occurs. So here, the estimated burst time of P4 is the least. Therefore, that is what is scheduled first. So this is what we discussed, and we also discussed one key question is in that how to estimate the next CPU burst time. So essentially, we understood that whenever we have to predict the future, inherently intuitively we look at the past history and then try to predict. Okay. So till now we have covered. Now let us move ahead with another variation of shortest job first. So the same algorithm, but now it is preemptive. So preemptive. So till now we were discussing non-preemptive scheduling. That means once a process is allocated the CPU, that process can go on running as long as it wants. However, now we will talk about preemptive scheduling. That means due to some other factors, the kernel can also preempt the CPU, a particular process. That means a process is made to give up control on the CPU so that the kernel can run and allocate the CPU to some other process. Okay, so basically a smaller CPU burst time process, say a new process has come with a smaller CPU burst time than the process which is currently running. Then this new process can evict the running process. So here is an example which I want you to work out. So you see here the four processes are coming at different times 0, 1, 2, 3, and these are the CPU bursts. Okay, so at time t equal to 0, only one process is available, P1, right, which has a CPU burst of 8 milliseconds. Now at time t equal to 1, P2 comes. Now P2 has a smaller burst time than say P1, the one remaining. So at time t equal to 1, P1 still has 7 milliseconds left in the CPU burst, 8 minus 1, but P2 has come with burst size 4. Therefore, according to the preemptive version of SJF, P1 will be evicted and P2 will be given the CPU. Okay. So I want you to take a couple of minutes and work out this example. If you have any questions, ask. Otherwise, please work out the example and give me the answer. And again, we are computing average waiting time. So yeah. Okay, any answers about the average waiting time? Okay, is anyone trying at all? Just say yes. Oh, okay, fine. Okay, Jayant is saying 17 by 4. Okay, let me wait for a 1 more minute just to see if any other answers come. Okay, some people are saying 26 by 4. Fine, let's see. Okay, so 26 by 4 seems to be the correct answer. Now let's see how things are happening. See, as I said, so at time t equal to 0, P1 is the only choice, so that is scheduled. Now at time t equal to 1, P2 comes and it has a smaller burst time than what is remaining of P1. Therefore, P2 is scheduled the processor. And in between, say at 2 and 3, P3 and P4 also come. But see, none of them have burst times less than P2. Therefore, P2 is allowed to run from 1 to 5. And at this point, at 5 t equal to 5, now see all processes are there. So P2 is completed, P1, P3 and P4 remains. So then the scheduler sees what is the CPU burst time of the processors. So what are the CPU burst times of the processors? 9, 5 and 7. Because P1 has already run once. So I mean P1 has already run for 1 millisecond. Therefore it is 7 and this is 9 and 5. So naturally P4 is given the chance. Then P1 because it had 7 milliseconds left, and finally P3. Right, so this is what you get. So see the waiting time for P1, how it is computed. Basically P1 is waiting from 1 to 10. So that is what is computed, 10 minus 1. Okay, so yeah, 26 by 4 is the answer. Good. Okay, if you have any questions, ask. Otherwise, let me proceed. Okay, so we discussed two versions of shortest job first. One is non-preemptive, another is preemptive. Now let us move ahead to another scheduling algorithm called priority scheduling. Here from the name itself, you can understand that some kind of priority will be assigned to the processes. So yes, some kind of priority is assigned to each process and the CPU is allotted to the process with highest priority. A priority can be based on many things. We are not going into a detailed discussion of that. So maybe priority can be based on actually the user running the code. So maybe the user running the process, if that user is more important, then that process is more important. Or depending on the application, you might actually have predefined priorities, like something, if some particular type of process comes, then that has to be given priority. So for example, I mean, again, intuitive. I'm not claiming that these things happen in the modern computer systems, but intuitively. Suppose there are broadly two types of jobs. One is batch processing mode. Just someone gives in some input and then the process runs for a long time and finally collects output. Versus there are some interactive jobs where the user is actually interacting with the system. So naturally the interactive jobs might have higher priority because if they are kept waiting, then the user keeps waiting. Whereas for the batch processing jobs, I mean, no one is waiting for the input. Maybe it is okay if the input comes in 2 hours. So something like that. Okay, so yeah, the priorities are important. Um, so yeah, and also again, this priority scheduling can be preemptive or non-preemptive, just like SJF. As you understand, suppose a particular process is running. Now another process comes in the system which has a higher priority. then will the running process be interrupted, or will it be allowed to complete and then the higher priority process should be assigned? That is decided whether based on whether the scheduling is preemptive or non-preemptive. In fact, some of you might guess that SJF, what we discussed earlier, is actually a type of priority scheduling, where the priority is defined as the inverse of predicted next CPU burst time. So if a process has a smaller next CPU burst time, then it has a higher priority. So that is what the scheduler will schedule first. Right. So in SJF, it's almost like the priority is decided based on time or the next CPU burst time. So here is another small example. It's too simple. I'm not asking you to work this out because every process comes at the same point of time and there is a CPU burst time and also there is a priority. So clearly the one with highest priority, fine. The one with highest priority will be assigned the CPU first and so on. So you can work this out later. I think the answer would come to 8.2 milliseconds, the average waiting time. Okay, now, of course, the key question is how to assign priority. There are two broad approaches, a static approach and a dynamic approach. So a static approach says that each process is assigned a priority, and that is like, I mean, right when the process comes, our process is assigned a priority, and that is what remains throughout the lifetime of the process. That is simple, this technique, but it has some disadvantages that there can be starvation or indefinite blocking. So suppose a kind of low priority process has been, there is a low priority process, but very frequently high priority processes keep coming to the system. So it might happen that this low priority process does not ever get chance to execute because very frequently high priority processes are coming. So this low priority process is never getting the CPU. This is what we call indefinite blocking, or it is also called starvation. Right? So basically every process is waiting for some resource. A primary resource is the CPU. Right? So if the process is not getting a resource for a long time, we say there is starvation. Okay, so yeah, static priority is simple, but there is this problem. So we go for dynamic priority. So before I go to the next slide, any idea like what? I hope you have understood the problem of starvation. So what do you think can be done to prevent starvation? How can processes be assigned priority?
So,
Yes.
so we can incorporate the waiting time into the priority.
Okay. Okay, but again, okay, the answer is good, but again, it would be better if you write in the chat, right? Instead of just speaking suddenly. Because if one person is speaking, it's guaranteed, then fine. But it can always happen that many people start speaking together. So I would like to avoid that. So it would be better if you write these answers in the chat. If you have something long to say, then just write a question or let me speak, then I can. I'll surely allow you to speak. Okay, but then, yeah, the answer that was given is correct. Somehow, suppose so. Two ideas. One is that make the priority dynamic. That means let it change over time. And one simple way of avoiding starvation is that if a process is waiting for a longer time, increase its priority gradually. Okay. So this is one approach of assigning dynamic priorities. Something called a response ratio is computed. And you see the formula here, time since arrival of the process plus CPU burst time divided by CPU burst time. So what does this tell you? If the time since arrival increases, Rn increases. That means this ratio increases. And that is exactly what you want. If a process has arrived quite early and it is it is waiting for a long amount of time, then its priority should increase a bit. This idea is called aging. So if a process is aging, that means if a process has been waiting for a long time, its priority, it's good to increase its priority a bit. Also, for a short process, if the CPU burst time decreases, the RN usually increases. Okay. What is the idea here behind this point? I think the idea behind aging is clear. I mean, uh, to prevent starvation. Our process waiting for a long time, it's increased the priority. But what is the motivation you think behind this second point? Or what is the idea? Okay, Ravi says SJF. So Ravi, can you unmute yourself and say what do you mean?
Yes, sir. So the process that has shortest remaining time will be getting higher priority if the CPU burst time is decreased. So
Okay, yes, true. But yeah, I mean, you what you mentioned, Animesh also mentioned the same thing. And yes, I mean, that is the idea. So if a process has only a small CPU burst time, the next CPU burst time is small one, increase the priority a bit because yeah, I mean, it's a nearly done processes. So maybe this process is already, I mean, it has executed for a long time, only a small CPU burst remains. Therefore, just increase its priority and let it execute. So yes, the idea is a bit like SJF in this part, right? So here we are trying to take care of both. If a process has been waiting for long, then also increase the priority. And if the process has only a little bit remaining, then also increase the priority a bit. Okay. Now, does Linux have a concept of priority? It does. So there is every process has a value called a nice value. And the nice value determines the priority. So a nice value ranges from -20 to 19, where -20 is the highest priority and 19 is the lowest priority. So by default, nice's value is 0. That means when you start a process, a normal process, it will start with a value of 0, nice value of 0. But then over time, possibly this priority might change. Also, there are two commands which you can use for setting or changing nice value, right? However, nothing to be very excited about because the bad news is that the user can only decrease priority of his or her processes. So otherwise, I think you understand what will happen. Everyone will say my process has the highest priority. So yeah, here a user can only decrease priority of his or her processes. Only the super user can increase priority of a process. Okay. So that is actually the idea behind the name also. So why should this value be called nice? Because you are being nice to others by reducing the priority of your process. Right. So yeah. So this, I mean, there is this concept in Linux also about priorities. Okay. So that was about priority scheduling. Next, we move on to another type of scheduling, which is quite popular, called round robin scheduling. So this is designed for time sharing systems. And actually, this is what we have been discussing most of the times before actually starting this chapter. So a small unit of time, which is called a time quantum or time slice, is defined. Typically 10 to 100 milliseconds. And the ready queue is a circular queue in this case. So the CPU goes around each process in ready queue and executes for one time slice. And there is a timer which is set to interrupt the CPU at the end of each time slice. So this is exactly what we have been discussing throughout this course before this particular topic, the scheduling topic. So there will be a timer and the kernel will set it and then give the CPU to one process. Now the timer is remember the timer is like it's attached to a hardware clock. So for the timer to decrease, there is no involvement of CPU. So the timer will decrease at its own pace, and after the time slice ends, it will interrupt the CPU. It will raise an interrupt. So naturally, to service that interrupt, the kernel will start running, and then it will decide which process to schedule next. So a bit more detail. So suppose a particular process has been allocated to CPU. Now two things can happen. One is that this process did not want to execute, let's say, for more than one bus time, even for one bus time. So maybe in between, as in it did not even execute for one bus time. Sorry, it did not even execute for one time slice. Before that, maybe it called for an IO operation or wait or something. So the process releases the CPU voluntarily, even before one time slice is completed. Second case is the process continued executing, one time slice completed, and then the timer interrupt came. So there was a context switch and this process is put at the tail of the ready queue. Now, in the first case, of course, we know that in this case, the process will be taken to possibly the waiting state because or terminated, as in the process might terminate before one time slice, or the process might start waiting for some child or waiting for an event. So it will be, in this first case, it will be moved to the waiting state. And in the second case, the process still continues to be in the ready state because it did not voluntarily release the CPU, it was preempted. Okay, so here is one example that if time quantum is 4 milliseconds, then what is the average waiting time? Let's assume that the schedule is P1, P2, P3. Can you work it out? So assume that the schedule is P1, P2, P3. Okay, Abhilash says 17 by 3. Okay, so Abhilash, Adi and all are saying 17 by 3. Yeah, it was pretty easy. So if you see, only P1 required more than one time quantum. Right, so yeah, P1 was scheduled first. At time t equal to 4, it was interrupted by the timer. Then P2 was scheduled, but P2 voluntarily gave up the CPU after 3 milliseconds. Then P3 was scheduled again. P3 voluntarily gave up the CPU in after 3 milliseconds, and then P1 was scheduled. Right. So yeah, so this is the average waiting time. Okay. Now for this, so this round robin scheduling is important because actually that is what is mostly used. Some combinations might be there, like some sort of aging, some form of aging or shortest job first, some flavor of that might be included in real life scheduling algorithms. But essentially in most modern computer systems use round robin scheduling with some variations, maybe based on process priorities or process ages and so on. So let us do a bit more analysis of this round robin scheduling. So let us say that there are n processes in the ready queue. Let the time slice be delta. So assume that each process gets 1 by n CPU time, but it does not get this constantly, continuously. This time is given in chunks, each of which lasts for time delta or less. Okay. So the maximum waiting time, okay, and there is the sigma, which is the scheduling overhead. So like every time one process is deallocated, one process is removed from the CPU, the kernel has to run, it has to save the context of the old process, it has to load the context of the new process. First the scheduler has to decide which is the new process to run. Then the dispatcher will load the context of that process. All this takes some time, a bit of time. So that is sigma. That is the scheduling overhead. So the maximum waiting time for each process is equal to n minus 1 multiplied by delta plus sigma. Okay. So yeah, I think this is pretty understandable why. Right. So yeah. Now there are two claims here. If delta becomes very large, then this almost becomes FCFS. Why? So yeah, any answers? So maybe Abhilash, since you answered the previous one correctly. Abhilash, so if delta is very large, it is claimed that this becomes almost equal to FCFS. Why? Okay, anyone?
Because the time slice is very large, so it won't there won't be any timer interrupt if delta is very large. So it's first come first serve only.
Sorry, why won't there be time interrupt? There will be interrupt after time slice delta.
But we are considering it very large as compared to the CPU burst.
Okay, yes. So basically, I mean, if the time slice is so large, maybe most processors finish within that time slice. So no process is utilizing the full time slice. So basically, whatever in the what order the processes are coming, basically they are getting implemented. I mean, they are getting executed in the same order, or because there is no like almost there is no preemption. So yeah. And okay, so you from this discussion you might think, okay, then if there is so much problem with large delta, then okay, let's have a very small delta. So that way this problem will be solved. It will no longer be FCFS. But then since you are decreasing the time slice, the number of context switches would become very large. And we don't want that because every time a context switch happens, there is this sigma scheduling overhead. So if you have many context switches, the overhead time would increase. Okay, so people generally choose some reasonable value of delta, which people have found out through experience. Like usually what kind of time slice works best? That people have figured out from experience. Right? But that is the problem with having delta as too high or too low. And typically delta is taken much larger than sigma. So sigma is the scheduling overhead. So remember what we discussed, that this scheduler should be very fast. So For example, if you see delta might be 10 milliseconds and sigma might be 10 microseconds. So the scheduling has to be that quick. Okay. Please mute yourself. Abhishek, I think you are unmuted. Okay. No, Abhishek? Okay. Okay. So yeah, so here is an exercise for you, which I would ask you to solve at home. So yeah, I mean, solve it. I mean, yeah, it's a standard thing to say, like, do this exercise at home, but now you are at home. So yeah, do this exercise maybe after the class. Yeah, so this is the four processes at arrival times at 0 and with this CPU burst times. So now this exercise asks you to consider various values of delta, which is the time slice, right? And then you will get to see the differences, as in maybe you will understand what is the difficulty or what is the problem in having delta very small versus delta very large. So usually something in between is chosen. Like too small delta is also bad because too many context switches, and too large delta is also bad because yeah, I mean things will like become similar to FCFS. Okay, so do this exercise later to get a feel of how does the delta value matter. Okay, we will move on to another scheduling algorithm. Multi-level queue scheduling. So just from the name, does it give any intuition? Multi-level queue scheduling. Okay, Vineet has given a good intuitive answer that maybe there are different queues with priority. Let's see. Sorry. So here, multi-level queue. So essentially the ready queue is partitioned into separate queues. Till now ready queue was just one, but we will consider now it is partitioned into separate queues. Let's say one queue for the interactive or foreground processes, another queue for the background or batch processes. A process is permanently assigned to a particular queue depending on the type of process it is. And each queue has its own scheduling algorithm. Okay. Because it is the designers understand that the foreground or interactive processes may have different requirements than say background or batch processes. So the picture looks something like this. Let's say the highest, so here the ready queue has four different sub queues. The highest priority queue is for the system processes. Next highest priority is given to interactive processes. Next for interactive editing processes. And the least priority is given to batch processes. So whenever a process will come, it will be added to one of these queues. And based on that, it will be decided how frequently that is executed. Also, as I said, each queue may have its own scheduling algorithm. For example, let's say a fixed priority scheduling is this: serve all processes from foreground and then from background. Okay. So again, remember there are two queues, let's say foreground and one for foreground processes, another for background processes. So the one scheduling can be that okay, maybe run something like say round robin scheduling on this queue first, the interactive processes, and once these are all processed, then go to the next, I mean lower level queue of other batch processes. Now, of course, there is this possibility of starvation in case of this happens, because the batch processes will starve. A slightly better approach is that fix some time slices. Like each queue gets a certain amount of CPU time, which it can schedule among its processes. So for example, 80% of the CPU time is given to the foreground processes and 20% is given to the background processes. Now the scheduling algorithm used in the two queues may also be different. For example, let's say the foreground process uses round robin scheduling because like every process there is interactive. So none of the processes should be kept waiting for too long. So let's say the foreground process uses round robin scheduling. The background queue, let's say, uses FCFS scheduling because it is okay. I mean, batch processes are like expected to wait for some time. So FCFS. Right. So different queues are using different scheduling algorithms. Also, the time is distributed among the different queues. So let's say 80% of time is allotted to the interactive processes and 20% is allotted to the batch processes. Okay, something like this. Okay. So that is multi-level queue scheduling. Now the last algorithm we will discuss is multi-level feedback queue scheduling. Again, any guesses? How can this be different? So here also there are multiple queues similar to the previous ones with different priorities. But what can be different? This feedback term has come. What can be different here intuitively? Okay, very good answer by Ashutosh. Yes. So based on something, processes can move from one queue to another. Yeah, also by Deep. So based on what that we are coming to, but basically in the previous case, let me go back a couple of slides. So in this, what we discussed, once a process is added to a queue, it forever remains in that queue. But now we are talking about a process can be moved from one queue to another based on some factors. So let's see. Yes, we allow processes to move between queues. So it is true that even now, say IO bound processes will be in one queue and interactive processes will be okay. I mean IO bound and interactive processes will be in the higher priority queue and maybe a batch process will be in a lower priority queue. However, a process waiting for too long in the lower priority queue will move to a higher priority queue. Okay, this is again the concept of aging. If you see, we discussed aging 20 minutes back. If a process is waiting too long in a lower priority queue, move it to a higher priority queue. So that is one way of avoiding starvation. So here is a sample algorithm which can be followed. We have three queues. Q0 is the highest priority. It follows round robin with time quantum 8 milliseconds. So delta equal to 8 milliseconds. Q1 has okay, yeah, Q1 is also executing round robin with delta equal to 16 milliseconds. And Q2 is executing simple FCFS scheduling. Okay, so when a process comes, okay, and the rule is this: a process in Q1 can execute only when Q0 is empty. Okay, so basically, what is going on here? Anyone would like to describe what is going on here, you think? So see the arrows. Can you understand what is going on? Maybe Ashutosh or Deep, if you want to give the answer.
So the time quanta for the three queues are different. So like first a process is placed in time quantum and queue that has quantum 8, then it is moved to 16, and then finally it is moved to the FCFS queue.
Yes, that is understood. But what is the philosophy? Like, why?
Yeah.
So suppose the first process, one process comes and it is placed, you are right, in this queue with quantum equal to 8. Then why should it move? Why should it be moved to the lower queue?
So, sir, suppose the program is interrupted by the timer interrupt, then the kernel knows that we need to give the process some more time, and so instead of maybe it needs some longer time, so it moves it to a higher quantum queue.
Okay. Fine. Okay. Yeah. Okay. So I think Ashutosh, the answer that Ashutosh wrote in the chat. Yeah, I mean, basically what was told is similar, but yeah, Ashutosh maybe put it a bit more clearly. The thing is, it is as if a kind of, the process comes, the CPU gives allocates it high priority. That means gives it in the first queue, and where it gets a time quantum of 80 milliseconds. If it finishes within then, great. So it takes this arrow out. So the process is done. If it does not end within within one quantum, then it's kind of a bit of a penalty. That means, oh, I gave you 8 milliseconds, you still did not complete. Okay, then move down the priority. So yes, next time it will be given a larger quantum, but the priority has been reduced a bit. And then let's say it is given 16 milliseconds quantum. It still does not finish. If it finishes now, fine, go ahead. If it still does not finishes, that means it has been given 8 milliseconds and then 16 milliseconds. So 24 milliseconds is a lot of time for a CPU. So if a process has not completed even with 24 milliseconds, then it moves further down the priority to FCFS queue. That means this is a long process. Right, so again here, shorter processes are kind of, given a bit more advantage, as in I mean, if the best would be if a process comes, it does not even take 8 milliseconds quantum and it completes execution and goes. If not, it is sure it will be given more time, but then the priority also comes down. Okay. Yeah, and maybe another rule can be that. So here are the sample rules that are followed. A process in Q1 can execute only when Q0 is empty. Also, a process in Q0 can preempt a process in Q1 or Q2. So these can be different policies that are followed. And yes, if the CPU burst of a process exceeds delta, it is moved to a lower priority queue. Okay. So here is a sample. There, a new process enters Q0. When it gets the CPU, it gets 8 millisecond time. If it does not finish in 8 milliseconds, you move it down to Q1. Later at some point it will get 16 milliseconds CPU time. If it still does not complete, again process move to further down to Q2 and so on. Of course, no solution is perfect, so there are issues here also. So for example, long running processes can starve. Okay. So permanent demotion of priority hurts processes that change their behavior. So let's say it can happen that a process had a lot of computation only at the beginning, but then it moved to a interactive mode. But in what we discussed, the moment, when the kernel sees that this process at the beginning is taking a lot of computation, it will move the process down the priority queue or to a queue of lower priority. So then if the next next part of the process is interactive, then performance will suffer. It's eventually, I mean, the issue with this scheme is that eventually all long running processes will move to the FCFS. So what can be done? Again, different techniques have been tried. One solution is periodic priority boost. So periodically, all processes are moved to the higher priority queue. That means say every process at some point, say, let's say, I mean, just picking some numbers out of the top of my head. I mean, these numbers are not sacrosanct. Let's say every 30 seconds, all processes are brought back to the highest priority queue, where all of them will get 8 milliseconds, right? If some process completes within 8 milliseconds, well and good. If not, they will again go down to the lower priority queues and so on. Okay, so this is periodic priority boost. Also, there can be another idea that priority boost with the aging. So this is something what we discussed earlier. Recompute the priorities based on scheduling history of a process. So if a process has already got, processes have already waited for a long amount of time, increase its priority by a bit, or bring it to the higher priority queue if a process has waited for a long amount of time in the lower priority queues. So yeah, so these are the different things that people have tried. There is no one solution which is always the best. And nowadays a combination of such scheduling is used. But yeah, I mean, typically we are discussing the different options. Fine, so that is what we will discuss for today. So basically we have discussed these 6 types of scheduling algorithms. There can be others also, but these are the 6 kind of popular ones. And modern day scheduling algorithms are somewhere a combination. That means as you saw in the multi-level queue scheduling and feedback queue scheduling, often modern computers use a combination of different schemes. So they may have different queues, and in one queue round robin is going on, in another queue FCFS is going on. Then there can be this aging, so increase of priority due to aging and so on. So usually a combination is used. And we also discussed how to evaluate between different, or how to compare between different scheduling algorithms. Usually we check the average waiting time of processes. That means how much time, how much time a process had to wait, averaged over all processes. Of course, like that also depends on the number of processes in the system. Like you cannot compare a situation where there are say 5 processes in the system to another situation where there are 50 processes in the system. So all those things do matter. But typically if you have the same situation, that means same number of processes coming at the same amount points of time, then average waiting time is a good way of comparing between different scheduling algorithms. Okay, I'll stop here today. Any questions? Okay, if not, thanks. We'll continue tomorrow. Thanks, everyone.